Helio combines the integration of two independent kinematic systems into a single robotic system. The primary robot consists of a 3 degrees of freedom steward platform that consists of 3 individual servos that are driven by an inverse kinematic algorithm to position the anchor points of the platform in terms of pitch, roll, and height relative to the base within the Euclidean space. The secondary robot consists of a rotational dual deflection paddle that is mounted on the boundary of the steward platform driven by a single servo. The goal, the primary robot is on the offensive, trying to deflect the ball off the platform, while the secondary robot is on the defensive, stopping the ball. The generated data is analyzed by AI model, measuring both performance and efficiency. The system architecture consists of the integration of 3 popular platforms, namely Python, Node-RED, and Arduino, utilizing their core strengths in synergy. Python manages the camera functionality, Node-RED provides the GUI or graphical user interface and centralizes the control management and data exchange between the various platforms, and Arduino drives the respective hardware. JSON or JavaScript object notation provides a compact, lightweight, test-based structure format for data exchange between the various platforms, optimizing readability and performance. SQLite, which is an open-sourced relational database engine, is used to capture and store the generated telemetry data, which can then be analyzed by AI to monitor both performance and efficiency. With reference to the primary robot, the base of the platform consists of 3 metal-geared, high-torque, high-speed servos which are positioned and orientated 120 degrees apart, minimizing the overall footprint, making for a compact circular design. 3 lightweight yet robust connecting struts are used to connect the base points to the anchor points of the elevated platform, with a design that aims for torsional rigidity with a low inertial mass, which was achieved through a hybrid combination of metal parts and plastic. Miniaturized bearings and brass bushings were used for the various joints to reduce friction, ensuring movement precision and repeatability. The Arduino board runs the inverse kinematics algorithm that mathematically calculates the required position and orientation of the anchor points relative to the base points within the Euclidean space, by articulating the connecting struts through their servo angles accordingly to target the required pitch, roll, and height. With inverse kinematics, we calculate the required joint angles to achieve the desired position. With reference to the secondary robot, the design had to provide for a rigid frame but had to limit weight, as the complete assembly is housed within the elevated platform that is articulated by the primary robot. The swing rotation of the paddle is limited to an angle of 170 degrees due to the underside connecting pins of the platform aligned along the primary x-axis. The 40-degree angle of the individual paddle itself along its center compensates for this rotational loss of 10 degrees to ensure ball reach across the x-axis on either end. The Logitech C220 camera is vertically mounted above the platform, while its USB cable is neatly channeled through the tubing. The controller enclosure is magnetically coupled to the platform base through 3 circular interlocking guides. A bubble level and 3 leveling feet have also been incorporated within the design. The complete assembled design is now shown with the Bamboo A1 3D printer in the background. All components were printed using standard yellow grade PLA. The platform is currently positioned at rest with a pitch and roll of 0 degrees, from which all random position commands will be baselined from. The primary robot is in offensive mode. receiving positioning data from node red, which sets its pitch, roll, and height parameters based on the JSON sample data format on the right. In manual mode, preset values are transmitted through to Arduino, while in random mode, randomly generated pitch and roll values between a preset maximum and minimum range are transmitted. Current pitch and roll values is shown on panel 2 on the graphical user interface. OpenCV, which is a powerful open-source computer vision and image processing library, runs on Python to provide for the object tracking and color detection capabilities applied to the source feed of the Logitech camera. Object tracking data is plotted in terms of the X and Y position of the ball relative to the overlaid grid, inclusive of radius from center and angle. However, this data is only transmitted if the correct green ball color has been successfully detected. A calibration grid is used to align the camera relative to the platform. The Python script is initialized by node red from the provided graphical user interface button. Object tracking data is then relayed firstly through to node red, which extrapolates and displays the respective data in terms of X, Y, radius and angle on the first panel. In defensive mode, the signal is then transmitted through to Arduino, which calculates the required rotational paddle angle accordingly to block the green ball from moving off the platform. The sample camera JSON data packet is illustrated on the right. On startup, an initialization run is executed to set servo limit synchronization with the Arduino controller. From there, run mode is initialized. Thank you for watching.